Hello and welcome to my continuing video series in asynchronous sequential logic. Today we're talking about hazards, and basically a hazard is a glitch or a quick change in a signal, and it should not be there. Hazards exist because of delays, the delays that signals experience when they're going through gates. First, some definitions. A static one hazard is when the line goes zero very briefly when it's supposed to stay at a 1 all the time, and it's shown there as a little diagram. A static zero hazard is the opposite. The line is supposed to be static at 0, and you get a brief glitch to 1 as shown there. The other and last type of hazard that we're talking about is a dynamic hazard. And a dynamic hazard occurs whenever you're getting a switch from 1 to 0 or 0 to 1. That's why it's called dynamic. And this type of hazard causes a brief pulse at the point where the switching is occurred. The diagram there is perfectly clear. We're going from 1 to 0, but we don't get a clean 1 to 0. We get a little blip, and that's called a dynamic hazard. Now consider the circuit shown there, and you will see how a hazard could possibly occur. If we change x2, it causes the input to this gate to arrive quicker than this input to this gate, because there is a slightly longer time delay as the signal has to go through the inverter circuit. So when we change x2, this one will change before this one. And as a result of that, there is a possibility for the output to have a glitch or hazard. Because this is a sequential circuit that has states, the hazard has the potential to cause a wrong stable state. There we've provided you with the transition table and the output map. Now from the transition table we can see that we should be able to safely move from total state 111 to total state 110. As you can see, that's a clear change with no change of output. We can easily switch back and forth between these two states, or should be able to switch back and forth between these two states by merely toggling the x2. When the x2 is 1, we're in this square. When the x2 is 0, we're in this square. But we toggle x2 between 1 and 0, and there should be no change of output. But that is not the case, because the hazard can cause it to go from here to here. So in other words, we have done something that we should not have happened. When we make the x2 0, instead of going here, we end up here. And since this is another stable state, we have got a 0 output now. And the biggest problem with the hazard is that it causes a malfunction of our transition table. When we should have gone here, instead we go up to here. So let's see how that would actually occur in the circuit itself. Well, this circuit shows that we're perfectly stable in 111. You can follow the ones and zeros right there through the actual logic and see that the logic is totally satisfied. It can sit there all day long. All day long it can sit like that. But now when we go to this diagram here, we see that because there's a delay in this inverter, when we change the x2 to a 0, instead of this one becoming a 1 like it should, it remains at a 0 for a small fraction of a second or whatever. This one has already gone to 0, which has caused this one to go to 0 up here. The output has gone to 0. And since this one hasn't yet switched to a 1, for a brief fraction of a time, we have 2 zeros applied to our NOR gate, which causes the output of our NOR gate to drop to 0 when it should not. Now, if the 0 comes around here and gets fed back into this gate, after this one becomes 1, this one will go back 1 after a small amount of time. Because we already have a 0 here, this gate is blocked. So, because this gate is blocked and this one is 0, the 0, 0 persists, and now our output is 0, even though we have a 1, 0 input. As shown here, we have a 1, 0 input, and we finally get that 1 on the output of the inverter that we want, but it's too late because we have 0, 0 applied to the NOR gate, and we have the output as a 0. This is what should have happened. We should have remained the output at a 1. So now with these two diagrams, this diagram and this diagram, you can compare what we should have had to what we get because of the hazard. Now, how do we correct hazards and get rid of them? Well, we have to insert a gate that will keep a 1 on the output when this situation occurs. So if we put in this gate here shown in orange, we will have the 1 from there, and we will have the 1 from the output prior to the fact that we change this one here to a 0. So we will have a 1, 1, and we will have a 1 that will keep this as a 1 during the short time that these both go to 0. So what we essentially happen is this is 1 and this is 0. This one drops to 0, but this one now, the orange one, keeps it at a 1. And then finally, this one now will come back up to be a 1 because of our inverter. Because the inverter will eventually take the 0 at x2, turn it into a 1, and we will have 1, 1 here, which will hold this at the 1. So we've completely corrected the hazard problem simply by adding this gate. What does that look like in the output map? Well, the output map is simply a Karnaugh map, and basically we're adding the redundant term that bridges the two terms that we have circled on the Karnaugh map. And when you do that, you get that. You add another term to the equation, and it's a bridging term, and we have labeled the gates 1, 2, 3, as you can see. 1, 2, 3. And down here we show what's going on. When we have 1, 1, gate 1 is 0, and gate 2 is a 1, and the output is a 1. When we make the x2 a 0, for a brief section of time, the delay causes both gate 1 and gate 2 have a 0, but now gate 3, our added gate, is keeping the output as a 1 until we get this 1, 0 established. And so the orange shows how, in fact, we have switched the two gates from 0, 1 to 1, 0, and how gate 3, our added gate, which is up here, has actually maintained our output at 1. So that's it. Thanks for watching, and we'll see you in the next video.